Next speaker is presenting a second work today. It's Dr. Marc Dupuy. Oh yeah, fourth?
Yeah, fourth, yours.
I present for you. Yeah.
And I'm presenting.
Okay.
Yes,
But presenting.
Yes, presenting, yes.
He has earned his PhD in chemical engineering in 1984. About pot ventilation. And
Yes.
his present position is consultant since 1994. And he does many mathematical modeling works and design about thermoelectric mechanical, CFD, and MHD of the Hauhero pots. Welcome, Dr. Marc Dupuy.
Thank you. So this is a little pet project of mine. I'm doing the work with Ibrahim Mohammed, that is now teaching at the University of Rochester. Before he did this PhD on dynamic stabilization of cell. That is an interesting idea that they had at Rochester University. And out of this collaboration, we decided to try to improve on the a mechanical model that was designed by Peter Davidson to explain how the electric energy is converted into mechanical energy in a simple system that was for him a pendulum. And for us is now a mobile because it's a better, closer representation of the cell behavior, because the metal pad is not hanging on a wire, but it is simply oscillation at the same level, let's say. So I will describe this mobile model. I will describe the calibration work, and then I will present a comparison of those results I'm obtaining with this simplified model with the one I'm obtaining with MHD Valdez. So the idea of this kind of toy is to find a sweet spot where you want to study with a better model. So you want to analyze the design space, and for us now it's only ACD and current density, but eventually we would like to include modulation of the magnetic field, for example. So there's a frequency, there's an amplitude, and try to see where is the best place to investigate with a better model. Okay, so stability is well, this is an explanation from him that we care about MHD stability, so noise. We need about mass balance, so chemical stability, and with thermal balance, so ledge motion, thermal stability. We want to squeeze ACD to be more productive, and then squeezing ACD is bad for stability. And then you have fancy tools like MHD Valdez or many other type of MHD models like developed by many people to study. But those models are normally very heavy CPU intensive, especially AluCell, for example. So you don't want to use those to investigate the design space because it will take a century. So you would like to get a tool to investigate this more faster. So the idea is to, okay, then other thing I need to introduce that my example is from 3-met cell in Hamburg, and this is down here. Those are the parameters that I'm using from that cell to invest, and then I'm gonna, in that work here, I'm gonna investigate change of the current density and change of the ACD that is called H0 in this academic labeling of things. So the magnetic field is a constant, so that's a weakness of this approach, I know. So that's one question out. and what I try to address this in this paper. Okay, so this is the mobile. So this is a plate of aluminum that is held on this pivot. And there's an imaginary material here that is conducting electricity the same way as the electrolyte, so bad, but it's not viscous. and there's no density at all. It's like vacuum, but conducting electricity like electrolyte. And there's a plate there, and the plate will want to oscillate. If we kick the plate, the center of gravity is not at the center at 0.5, but it is moving. It is a parameter, because if I don't do that, it's too stable. And so this is the device, and then this device, if there's no current, you kick it. There's a friction also. Now it's addition of a friction, so that there's a kind of a damping mechanism. So if you kick on the thing without magnetic field, it will simply stabilize to the initial position. If there's current density is enough, depending on the CD and H and metal pad and then magnetic field, it will amplify or decay. So you kick on it, you get an angle. It will convert from it's a thick plate, so it can only oscillate what we call a 1-0 mode or a 0-1 mode in the other direction. That's the only two modes allowed, because it's a rigid structure. But if you kick in one direction, it will the current will, like it's happening in a real cell, will transfer the motion to the other direction. That's how you get the oscillation. And this is the equation of this system. That's so simple that you can, if you have a physicist, he can come out anyway. Somebody who's good with this kind of analytical analysis, you come up with the equation. So there's a damping coefficient. You have two frequencies that are the natural frequency of this thing, and you have alpha, or that is coming from the coupling with between mechanical and magnetic field. So you have the BZ, you have the G0, the current density, and you have N, that is this new parameter, that is the position of the center of gravity. And you have one parameter that I think I overlooked in the past is the density of the plate. I'm using the aluminum plate density, and maybe that's why I need to move the center of gravity higher. If I would be using, now I'm planning to use next work, is the difference of density between the bath and the metal. So the thing will be more stable without having to move the center of gravity. But that's future work. So now, so if you use the 3-meter cell as to get your dimension, last year I calibrated for critical stability at 4.3 centimeter ACD by first adjusting the damping to get 90% damping of gravitational oscillation, and then you adjust the center of gravity to get at condition of operation to get critical stability at 4.3 centimeter. Now I've done something different this year. I first find the position of the center of gravity without friction for the full size, and then we cut in two the plate, and we're now considering only the oscillation of half of the metal pad. So the plate is now not the full length, but half of the length, so that a 1-0 mode in that mobile model, it is a 2-0 mode in the actual cell, and the magnetic field of that model is now only magnetic field on one side of the cell. So like now we're using 30 Gauss, that would be the magnetic field on one side of the cell, and if it's symmetric, then it will be minus 30 Gauss on the other side. So that's and if we are doing that, then we need to adjust the friction coefficient differently. I'm getting this number now down here. So of course, after this calibration, I'm back to critical stability at 4.3 centimeter ACD. Now, next point is that if you solve the two equations, then you're gonna get, depending on the setup, you're gonna get a growth like I'm getting here, and then you can fit this growth to get the growth rate like this. But now this year we're doing differently. We're doing a linear stability analysis, so we're converting into assuming this behavior here, so exponential growth with this omega that is the complex number for. So the frequency is the real part, and the imaginary part is the growth rate. And then if you do the algebra, then you have to solve this equation, this long equation. You find the root of this equation in complex space, and then you get your solution. So you can use, like he's doing, you can use MATLAB to solve this, or you can use even what I did as I use Excel. Excel can cope with complex number, so you can convert the root of this equation in Excel, and then the parameter of the equation are coming from the dimension of the cell. And what I'm doing here is that I'm playing with the current density. The number are here around from 0.72 to 0.84, and I'm playing with the ACD from 3.5 to 5. And then you solve this equation for each parameter changement. Then you get this solution in like a second. You have this map. So you have all those, and each number is a growth rate. So when it's red, it is positive. So it is going. It's unstable. This is the critical point where we have calibrated, and all the red, the green is where you are stable. Okay, so this I get in a fraction of a second with this model. You can also show this way. It's a smooth surface. You can see by that it is more twisted here than down here. There's a curve here. It's not a straight line from here to here. So this is a 2D design space of this problem that you will never. What previously I said here there's a 112 point that was analyzed only with 2D space. Imagine if you go 3D space, 4D space, 5D space. So you cannot investigate this kind of space if you don't have a quick answer. Now, okay, how good are those numbers? So next, I'm using MHD Valdis to test only 7 points, because every point it's an overnight run to get one number. And the way we need to get a growth rate out of MHD Valdis. This morning I showed that I'm getting one, but it's a bit too crude. It's only considering 2 peak and then fitting the growth on 2 peak. Here we are extracting from the steady state solution. This is the wave after some evolution, and if you subtract this from this, you get what is actual wave motion. And if you do a RMS fit on this amplitude of this wave, you get a single number each time step. Not every crease, but every time step. And then you fit, so this is the condition where it is stable, so it is decaying, and this is the condition where it is unstable, so it's growing. Now, the issue about when you try to assess this kind of number with MHD Valdis, if you are in a very unstable condition, you will get the short circuit quite quick. So quick that you cannot assess the growth rate well. So that means that for very unstable cell, the prediction of the growth rate is more noisy or inaccurate. So those are the number I got after a week of work for those 7 cases. Now, how do they compare with what I was predicting with my mobile model? They are all within 95% confidence rate. So, and the more the highest I'm getting, it is very unstable case. So I have not done this corner here, the 8 point and the 9 on top here. I have not done because it's all too stable also to get the good fit for the damping. But anyway, I have 7 points, and all 7 are very close to the map that I got with my mobile model. So for those 2 parameters, it is a very good tool to investigate design space. But so we are confident for those 2 parameters, this mobile model is working well. We have tried the metal pad, and it's not working so well. So I need to work more on the metal pad. And the magnetic field I have not investigated yet. So that's, again, future work. But ultimate goal is to be able to I hope that I can eventually investigate the dynamic stabilization, so modulating the amperage of a compensation loop, and to find what is the frequency and the amplitude of that modulation to stabilize the point better than we are doing now. So that's it. Thank you very much for your attention.
Questions?
Hi, I'm Robert Chain from Rio Tinto. Just a question about the computational time. What is the more or less like for the AP18? Oh, sorry, not AP18. For the 180 kiloamps cell here.
You mean MHD Valdis or the mobile?
Your mobile.
Mobile, it's
like a couple of seconds.
no,
right?
it's too fast to measure, I think.
Okay.
Yes.
And so far, so I understand at the current status of it, it is ready to calculate more or less stability.
It is calculating stability.
Yeah, okay.
Well, for ACD change and for current density change.
Okay.
But
Was thinking the application industrial, so I understand.
at this point, we don't have a really application.
Maybe squeezing test or that's it.
Yes. So if you want to validate, but it's the same issue as validating MHD Valdis. Yes.
Thank you.
So I have a question, Mark.
Yes.
The magnetic field is a constant field, right?
Yes.
So it's like the average of the neighbor cell field that is impacting.
It's average of, if you have a BZ shape like they have in Trimet, there's a big deep hole and upstream corner, both upstream corner because of the design of this bus bar.
Yeah.
So you have to average this to a single value.
To a single value.
Yeah.
Did you variate this value to see the impact?
Not yet.
Not yet,
No.
but okay, I suggest you to do it. It could be interesting.
Ibrahim is busy now. He's a full professor at Rochester University.
No, I understand.
Now that I've developed the same with Excel, I will probably do more work myself. Before I was relying on him because he has MATLAB, I don't. But I don't need anymore.
Someone has a question? Because I have another question.
Oh, yeah.
Have you considered to use this to feed an AI and to optimize something?
We should have a paper on this next year.
No? No, it's just asking because
Yeah,
it
No,
also would be interesting.
I don't have access to an AI, so no, I have not considered.
Okay, but
Yes.
maybe someone is going to try.
Yeah. Well, you see, I'm giving everything. You have the equation. It's easy to solve. It's so easy to solve. If you take an hour, if you're good in Excel, you take an hour, you have your model.
More questions? So let's thank Marc Dupuy for the presentation. Thank you.